action.
Hi, this is Wei Dai, and today I'm gonna try to show some application of convex optimization. And what I want to talk about is Bi-criterion formulation. In mathematical way, this is to minimize with respect to, for example, in two-dimensional ax minus b and x norm. In this example, we want to minimize there is two terms. One term we can call it data fidelity term. This is ax minus b, and another term. This is about our prior knowledge of the data itself. First of all, we can write it as a optimization problem to minimize ax minus b plus lambda times x, and for simplicity we just use L2 norm, and in order to make it computation efficient, we write it as this one. This won't change the results. So the first thing I want to mention is there is a trade-off between the bi-criteria. And what I mean the trade-off is, here we want to minimize this term with respect to two issues. Assume one is data itself, another one is the ax minus b. If we use different lambda, the trade-off curve will look like, well, in this shape, but this is just an example. We can see if data itself is 0, so what we get will just be the optimal value will just be b, because x equals to 0. And for the other direction, we want to minimize the x norm as much as possible, but usually we cannot make the ax minus b equals to 0 because of the reality. So this is the trade-off. Secondly, I want to show how to solve this problem. And we can notice that this is a convex optimization problem, and because we use L2 norm, make it square. If we make the L2 square, this somehow can be represented as the power of the signal. Now we just take this as an example, and we see this is L2 norm square plus L2 norm square, so it's not only convex optimization, it's also differentiable. So the optimal condition is to, if we let the objective function equals to j, we need the derivative of x to x equals to 0. So what we get will be, let me write it down, times 2 minus a plus b, a plus b plus lambda x transpose x equals to 0. This will be 2 times x transpose A transpose A x minus x transpose A transpose B minus B transpose A x plus B transpose B plus lambda x transpose x equals to 0. We take derivative of it, so it will be 2A transpose A x, there's no 2, minus A transpose B minus A transpose B times 2 lambda I x equals to 0, which is A transpose A minus A transpose B x times 2 lambda ax equals to 0. The answer is x A transpose A inverse, because this is we assume it is inversible. Oh, not this one. X equals A transpose A plus 2 lambda I inverse A transpose B. This is the answer for this problem. So now I want to talk about some interpretation. Why I think this formulation is important and useful, because assume we observe a data which is y. The data comes from, I write it as convolve with the input signal, and sometimes, usually, always we will have some noise. And we can write the convolution into in the matrix form, which is A equals A matrix A times X plus N. So we want to reconstruct our data, which is X, but we only know Y, and we may know some property of the noise, but not exactly. So the problem will be difficult if we only consider the first data fidelity term. We try to minimize this term. But what if we know the signal itself is smooth? And what the smooth I mean is like the data will not vary rapidly. Not very rapidly. So I want to introduce a matrix which is D. Matrix D is in this term. Other entries are just 0. Dx means the signal itself is smooth. This is the prior knowledge we know for this example. So what we want to minimize will be with respect to X. This is data fidelity term, and this is the penalty term. The penalty term is get from our prior knowledge, which is the signal itself is smooth. So as we can see, this formula is similar with the first problem we talked about the Bi-criterion formulation. So this formula can be used to do denoising because this term we can interpret a times x minus b. We can know that here the b is y in our example. So it will be noise. So we want to minimize the noise as much as possible, and the signal it's smooth, and this is also convex optimization, and it's differentiable. So we have closed form for it. So let me write the closed form for this problem. The answer will be in terms of this. So at this point, we know how useful the optimization it is. It can, of course, it can be used to a lot of different fields, and it's a powerful tool. And also, just for the criteria formulation, I want to write it down again, just to make it clear. This is just a norm. Now it's not a L2 norm, and we have another term, and I make it like this. Now it's not just the smooth, the matrix D we used before. It's another one. We can make the penalty function by our prior knowledge, which can be different. Previously, we used L2 norm. We can also use L1 norm. If we use L1 norm, we can improve the sparsity. The sparsity is like this. For example, if we have L1 norm, the penalty function will look like this. If we use L2 norm, the penalty function will like this. If we use L2 norm, we give less weight for the small values, but if we use L1 norm, we will give more weights for the small value. So we will make the signal more sparse than using L2 norm. But for the L1 norm problem, the problem is, for the data fidelity term, we just use L2 norm, but for the signal penalty term, we use L1 norm, and here we just use the X, which means our signal is sparse in this case. But although we see this is convex, but it's not differentiable. So we may need to apply other methods to get the answer of this term. There's no closed form solution. We may use, we can use the MM algorithm to make the L1 norm term be differentiable. There are also a lot of other algorithms can be used to solve this problem, but I think for now, that's it. Thank you.